So let's take another case to illustrate this. Any questions over this so far? Yes, Helen?
So it really doesn't matter what the first derivative is.
Yeah, the critical thing is whether the second derivative is positive or negative at the critical value of x. So there might be cases, Helen, where the second derivative is negative, but it's not necessarily constant. But that would still guarantee a maximum, a local maximum. Okay. Let's consider another case. In fact, let's just flip this function around. Let's take this function here. Let's use the same equation, but let's make this a plus x squared. Okay. Now, the first derivative is what? What's the first derivative? Anybody? Okay, it'd just be 100 plus 2x. So if we wanted to find the critical value of x, we would do what? Oh, well, wait. We'll get to the second derivative, but let's assume we want to just find the critical value of x first.
Set the first derivative equal to 0.
Bernard, yeah. Just set the first derivative equal to 0. If we set this first derivative equal to 0, notice we'll have 100 equals a minus a 2x, or x of 0, the critical value of x equals minus 50. In this case, our critical value of x is minus 50. And what is the stationary value of the function? What is f of 50 going to be in this case? Okay. Yeah, it would be 5,000 plus 2,500 be 7,500. Okay. Oh, thank you. Thank you. Actually, it should. Thank you. Thank you. Ben, I'm so trusting that you're going to give me the right answer. I just assumed. Yes. Thank you. Who told me that? Rebecca? Thank you. So it would actually be, yeah, this would be minus 5,000. What's that? Okay. So, yeah, minus 5,000 plus, minus 50 squared would be 2,500. So Ben is generally right. So this would be minus 2,500. That's okay. That's what calculators are for. We would have discovered it soon enough anyway. So, from what we know already, we know the general shape of this function, don't we? This is a quadratic function, and it's going to be U or upside down U? It's going to be U-shaped because the coefficient of x squared is positive. And we know the vertical intercept is 0, still 0. If x is 0, y is 0. So we know this. It's U-shaped, and furthermore, we know at this critical value, minus 50, the stationary value is minus 2,500. So we really know how to graph this already. It's going to look like this. It's going to be U-shaped. It'll look like this. And right here, this has to be where x is minus 50. Because that's our critical value. So the slope right there has to be 0. Furthermore, the stationary value, the value of y, has to be minus 2,500. That's this value right here. Okay. All right, so that's what its shape looks like. Interestingly enough, in this case, what is the second derivative? Okay. Here was f prime of x. Forget about this equaling 0 for now. Yeah, it's 2. So in this particular case, the second derivative is always positive. It's positive and equal to 2 at every value of x. So at this point right here, what do we have? At x equals minus 50, the value of y, the stationary value of y is it's a minimum. Yes, it's a minimum. Okay. And what does it mean for the second derivative to be positive? It means that x and the first derivative move in the same direction. If x increases a little bit, the first derivative goes from 0 to positive. If x decreases, the first derivative goes from 0 to negative. So that's why this second derivative test determines whether you have a minimum or a maximum, because it tells you what the curvature of the function is. Whether the curvature of the function around the critical value of x is concave or convex. Okay. Okay, so this point right here, minus 2,500, is a relative minimum. Okay. So let me just summarize what we learned so far. In order to have a maximum, the first derivative at the critical value of x has to be 0. And a sufficient condition, this is the second derivative test, a sufficient condition for a maximum is that the second derivative be negative. If you have this pattern, 0 first derivative, negative second derivative, that guarantees a maximum. Okay. For a minimum, what you require is that the first derivative be 0, and a sufficient condition for you to have a minimum is that the second derivative be positive. Okay. So this configuration right here is a sufficient condition for a maximum and minimum. First derivative be 0 in both cases, and for a maximum, second derivative be negative. For a minimum, second derivative be positive. And this is referred to as the sufficient conditions for a minimum and a maximum. Now, the only problem with this test, the only difficulty with this test is when the second derivative is neither positive nor negative. If the second derivative is 0, then this test will not tell you what you have, and you have to do some further work. But in most cases, what you'll find is you'll be able to sign the second derivative. So this test will tell you what you have in most cases, except for the rare case where the second derivative evaluated at x sub 0 is 0. Then you have to do some further testing. Yes, Preston.
Second derivative is 0, that means that you have to go maximum 1 minimum.
Well, you could.
But you can't have an absolute maximum.
Well, okay. We're discussing a couple of concepts. If the second derivative were 0, you could have a local maximum or you could have a local minimum there. You won't necessarily have that, though. You'll have to do some further investigating to see. Let me illustrate this point with an example. In other words, if you find the second derivative is 0 at the critical value of x, you don't know what you have. It could be a max, it could be a min, or it could be neither. Let me illustrate with an example. Suppose we have this case right here. Y equals f of x equals x cubed. Okay. What is the first derivative? Three x squared. And what would be the critical value of x? 0. If we set this equal to 0, the only way 3x squared is going to be 0 is if x is 0. Okay, so the critical value of x is 0. Okay. What is the value of the second derivative? What is the second derivative, just in general? The expression for the second derivative is 6x. Now, what you're supposed to do, this is an interesting case. See, the second derivative is not constant in this case. So what you need to do, you need to evaluate the sign of the second derivative at the critical value of x. What is f prime of 0? The 0 is the critical value of x here. And that's what's important. What is f prime of 0? 0. So in this case, our second derivative test wouldn't tell us what we have. Okay. But in this case, what do we know just from the graph? What is y equals x cubed? What does its graph look like if you were to graph this? Anybody? Well, what does this shape look like?
First quadrant, x squared.
Yeah, it looks kind of, yeah. It looks kind of like that. Exactly. So in this case, our critical value of x is 0. Our stationary value of y is 0. And we have neither a minimum nor a maximum here. What we have here is an inflection point, which is neither a minimum nor maximum. So in this case, we have neither a minimum or maximum. But I could construct another example, and I will on Friday, where the second derivative is 0, yet we have a maximum. And I could give you another example where the second derivative is 0, yet we have a minimum. So in general, if you find the second derivative is 0 at the critical value of x, you have to do some further investigation to figure out what you have. Okay.